So, hello friends. Today I am going to discuss the drawdown testing. But before discussing this drawdown testing, I want to just recapitulate some idea of doing the build-up test. Now, as you know that this build-up test have been performed earlier from our earlier discussion, that this build-up test are actually gives us some idea about the reservoir properties, reservoir boundaries, and distance of the reservoir boundaries, as well as we can able to find out the reservoir size. Okay, so in this way this build up data is very useful, and there are strong reasons why we do this build up test. The reasons are: number one, the math is quite simple for zero rate. Everybody would agree with this, because the rate that we consider for build up test is zero at the time of shut in. Whatever rate we consider for our calculation purpose are the rate or the rates of the past productions. So generally in Horner approximation we consider the Q last and the pseudo producing time. So all of these things we have already discussed. We are not going to that much detail. Number two reason which makes the build-up test quite useful for us is that the data tends to be very smoother, because we have just zeroed one of the parameter, which is rate, and therefore what is coming is only pressure, which is to be recorded with time. Therefore the smoothness of the data is very good in particularly build-up test. So once you are able to plot the derivative type curves matching, what you will see that the derivatives are very sensitive graphs, and if the data are not smooth, this data derivative type curve is about to fluctuate and will give us the error in the results. Okay, and difficult to interpret. Therefore the data needs to be very smooth, very recorded in good conditions. So equipment should be robust, everything which makes the build-up test quite good. Number three, it is quite easy to execute the procedure, right? So you hook up the gauge, shut in the well, you place the tool bottom hole, and you can record, right? So not much, it will not uh, make you pain in recording the data, gauging the data. So overall it makes the build-up test quite useful. However, if we understand this build-up from the cash flow point of view, what we'll see that this build-up requires the well to be shut in, which means that there is a delay in production, right? And the production is directly related to cash flows. So understand, if the shut-in time is going to be very large, then the revenue generated will go down, right? Also, the management approval to run a build-up test can be easily obtained when the well is going to be shut in anyway due to some kind of pipeline or facility maintenance, some kind of slack demand you have, or movement of the rig, right? So the well is going to be shut in anyway. In any case, just record the pressure and try to learn something about the reservoir. So whenever the well is in certain condition, it is a good opportunity for the engineer to understand that data, right? This data tells you a lot about the reservoir. Another thing about build-up test is that uh, it is an opposite of drawdown testing, right? So in vice versa, we can say this drawdown testing is opposite of that of build-up test. So now in next slide, we'll be discussing about drawdown testing. So before going into much detail of the drawdown testing, we must understand few things about drawdown. Number one, that the well is produced on a fixed choke setting, right? So choke need to be fixed at a condition where the pressure of the upstream to that of downstream is around 2 is to 1. Or in other way around, we can say that if the downstream pressure to the upstream pressure ratio is around 0.58 to zero point 0.6, right? So that type of choke setting needs to be done, and in that case what we'll obtain is the critical flow. Now once you have the critical flow, we'll have the constant flow rate, right? Irrespective of the disturbance on the downstream side. So whatever disturbance which is taking place on the downstream side, the upstream pressure and the downstream pressure ratio, if it is comes around 0.58, then the flow that we are getting will always be constant, right? And that particular constant flow rate that we need actually for this drawdown testing, right? So we always need to fix the choke setting in order to obtain the constant flow rate, which is the necessity in case of drawdown testing, right? It is also called single flow rate testing. Next thing to remember about drawdown is based on rate of pressure decline. If the choke is adjusted anyway, the rate of pressure decline will be adjusted too. Therefore, it will make the well test interpretation less reliable. So therefore, these are certain things which need to be remembered for drawdown testing. This drawdown testing is also a constant choke testing, not a constant rate testing, right? So by mean of constant choke condition, what you will do, you are making the rate constant. However, with time, the rate may not be constant. It depends on the downstream and upstream pressure. So if upstream pressure goes down, actually the flow rate may change with a period of time. Therefore, the concept of multi-rate testing has originated, right? Now in drawdown testing, what we do is we produce simultaneously and test, right? So both test and production goes hand in hand in drawdown testing. So there are some advantages that we have discussed, and in this slide we'll also highlight those. So in build-up test, as we see that the revenue goes down. However, this drawdown testing, we do production as well as testing hand in hand. So the management sees the cash flow, and they generally recommend such kind of testing which will give you the insight of the reservoir as well as the cash flows, right? Also, these data are very useful for reservoir engineers because these data gives them reservoir size. So we have put some calculation based on estimating the reservoir size out of this drawdown testing. We'll discuss in some coming slides. Also, the production engineering evaluate the completion, and for completing the well, the data need to be gathered which comes from this type of test. Drawdown testing evaluates the well reservoir at production condition. We already discussed in our previous slide. In case of multi-phase flow, this is very important. In case of multi-phase flow, if the reservoir or if the rock is highly compressive, there can be significant differences between a build-up response and drawdown response. So it is the multi-phase flow which is causing difficulties in two different type of test. So drawdown test or drawdown response is mostly affected by such kind of test, right? So now it is affected by multi-phase flow. Therefore, this drawdown will be likely to be more valid in certain conditions where the real picture is coming out of the test, right? Now, sometimes, or in most of the times, this build up and drawdown test are done in succession. The reason being is that if the analysis of pressure build up and drawdown are coming to be same, then there is a greater confidence in the results, and the outcome that we are discussing out of these two tests will be more sure about that, right? So this particular discussion has been taken from Halliburton PDF that I downloaded, and the topic was type of well test, build up and drawdown. Okay, let's move ahead. Now, what is drawdown test, right? Till now, you must have an idea what is a drawdown test. It is opposite to that of build up. First of all, I want to mention that. Now, initially there was a shut-in before producing the reservoir, and the shut-in is been done to maintain the pressure stabilized, right? Now, once the pressure is stabilized, will allow the well to flow at a constant rate. Okay, so this is a drawdown test. Now, what we estimate out of this test: the permeability, the skin, reserve volume. These tests are particularly applicable for new well, exploratory well, right? Now, if I talk about exploratory well, we want to find out the fluid properties as well. So if we could produce the fluid from the reservoir, the fluid property can be known, and also the volume of the drain of the well, volume of the drainage area can be easily estimated, right? And is also not led to any kind of revenue losses as that of build-up test. So in many ways, this type of tests are very important. However, there are the cases where the constant rate maintenance is very difficult, right? So if we want to maintain the constant rate throughout, it is very difficult. Therefore, the concept of multi-rate test has been emerged. Now, as you can see the equation 1, this equation is generally written for a well flowing at a constant rate for a t period of time, right? So the t is actually the time of production. So this is the pressure distribution which is shown by equation 1 for drawdown testing. I would mention that please remember this equation because this is most of the time required in calculations. Now, as far as the flow regime is concerned, in a similar fashion as we have seen in build-up test, we have three different flow regimes, right? One is early time region, middle time region, and late time region. Now, in early time region, the flow is mostly dominated by well-bore effects, right? And we want that whatever the fluid flow is taking place at the surface should be equal to the rate of fluid enters into the wellbore, right? And once these two rates are equal, then only the wellbore storage effect will go. Otherwise, the wellbore storage will be dominating and will not allow the middle time region to reach, right? So most of the time this early time data is not useful and it will distort your middle time region. It will not allow the middle time region to reach as fast as possible. So our always the objective is we want the rate at the surface and the wellbore to be equal, right? Now, duration of wellbore unloading can be estimated qualitatively by log-log plot and using the type curve empirical correlations. We have different type of type curves and these are very well utilized for estimating the wellbore domination effect and the middle time region. Late time region begins when radius of investigation reaches a portion of reservoir influenced by reservoir boundaries or massive heterogeneities. So this late time region can be easily demarcated once we have the pressure drawdown data. We plot it on a different type of graphs and we can easily demarcate this late time region, early time region and middle time region. It is log-log graph and type curve which will allow us to clearly see such kind of flow regimes. Okay, so as you can see here we have equation 2, which is the dimensionless time, and CSD is the well bore storage constant, dimensionless constant. So it is very critical parameter which need to be evaluated before the reservoir properties has to be estimated using type curve. So CSD is very important, and TWBS, that is the time for the well bore storage to end, is given by this particular equation, right? So analytically the expression is this one, equation 3. Now this middle time region is very important. As I said, different properties can be evaluated. Once we know the slope of middle time region, we'll be able to evaluate slope, and then once we have the value of slope, we can easily find out the permeability of the reservoir and as well as skin factor. So this region is quite important. And as far as you have seen that this build-up test that we have performed earlier and the data that we got from drawdown testing are almost giving similar kind of graph, and interpretation is also similar. However, some few equations are different, right? Now, time required for the late time region to begin for a well-centered in circular drainage area is given by this equation 7, right? So you need different properties of the reservoir, area and K, right? So this would be the time required for the late time region to begin, right? In case of the well centered in circular drainage area. However, if the shapes are complex, right? For complicated shapes, similar exercise as we did in unit 1, table 1.2 is used to estimate the time for which the reservoir is infinite acting and the time for which the boundary effects are felt, right? Okay, so you can see this figure 3.1 here. You can see this is the early time data of the drawdown testing, which is actually not useful and is distorting our middle time region. Now this middle time region has to be identified for knowing the different reservoir properties, and this late time region is actually telling about the boundaries and various reservoir heterogeneities. Okay. Now this data which is coming out of from drawdown testing is also useful in estimation of pore volume. I recommend you to go through example 3.1 John Lee textbook, where the data allows you to calculate the pore volume of the reservoir. If you recall unit 1 pseudo state solution, page number 6 of John Lee textbook, there what we did a differentiation with respect to time for the solution that is coming out of pseudo steady state solution, and we arrived at an equation which is similar to equation 9 shown in this slide. Now what you can see is that this equation is showing you the relationship between slope of the drawdown curve and the relationship between slope and drainage area volume VP. So from this equation, if we can evaluate the slope of the data in the region, particularly middle time region, this data will give you or allow you to estimate the VP, that is pore volume of the reservoir, and is very useful, right? Okay. So as I recommended you, please do the example 3.1 from John Lee. So the data which is there in table 3.1 I brought up here. Here you can see that time, pressure is given, right? So the pressure drawdown with time is given. These are the various properties, other properties which are needed to be used in this particular solution. So what you have to do here, you have to estimate the formation permeability and the skin. Also, you have to find out the pore volume. So initially what we do here in step 1, you have to plot this data in simple Cartesian format, and you will see the quite deviation in initial region, this is ETR region, and in late time region. So this particular region is the middle time region, right? So this is not Cartesian, sorry, this is between Cartesian and semi-log. This is semi-log graph of drawdown testing. Now the same data if you plot in log-log curve, where on the y-axis you have delta p and on the x-axis you have time. So this is a log-log curve, and to find out the time up to which the well bore storage is dominated, if you can see this graph, you cannot say this point or this point, right? So such type of graph should be superimposed in the type curve to find out exact value of the time at which the well bore storage ends, right? So here the interpretation is quite difficult, as you can see in this figure. It is difficult to say where the well bore storage has been end and where the boundary effects begin to start, right? So using the superimposition principle, uh, this graph can be superimposed on the type curve, and various properties can be evaluated like well bore storage, skin, and reservoir permeability, right? So as you can see here, in this step we find out the slope of this graph, and the permeability is found to be 7.65. Now in step 4, what you can see that the calculation says that the uh, early time data or the well bore distortion ends at 12 hours. So using radius of investigation, we saw that up to 427 feet, right? Up to 427 feet, the pressure transient has moved, and all the data is actually well bore storage data. So up to 427 feet, we cannot evaluate different reservoir properties. From 427 feet onwards, up to 1510 feet, we have this middle time region where the reservoir seems to be infinite acting and there is a radial flow. Therefore, this region is quite important for evaluating different properties out of this reservoir. In step 5, what we did, as we did in build-up test, same equation is used here to find out the skin factor, which is coming to be around 6.37. In step 6, as I said, CS is the uh, well bore storage coefficient, CS, which is found from different properties such as area of the well bore and density of the fluid, which is coming around 0.0106 barrel per psi, and the time of well bore storage ending coming to be around 4.47 from this particular calculation. So therefore the graph says that 12 hour and this particular calculation says 4.4 hours. So we need to take the help of type curve to actually estimate the time up to which the effect of well bore has been dominated, right? Let's move on. Now let's move on to multi-rate test. Here what you can see that whatever we discuss here, we'll be talking about infinite acting reservoir and slightly compressible fluid, right? So our discussion is limited here up to unit 4. After that, when we move to gas well testing, we'll see how we do multi-rate testing for gas wells. There are slight changes in the equations, and those equations are actually used for multi-rate testing in case of gas well. But here I want to emphasize some points. What is the need for this type of test, right? Now in second point, you can see that sometimes it is very difficult to maintain the constant rate in case of simple drawdown. In simple drawdown, we generally say about the rate. We say about the rate is constant, right? So if we see physically, this is not true. The rate is variable, and maintaining a single rate is very difficult. And therefore, if you want to estimate the real conditions of the reservoir or real properties of the reservoir, you have an understanding how the multi-rate test can be estimated properly or can be taken properly to estimate the reservoir properties, right? So this need to be understood. Another thing that in gas well we have two different kind of skin. One kind of skin is a skin which is due to the formation damage, right? And other kind of skin is due to turbulence near the wellbore, right? So this turbulence near the wellbore due to the high flow rate near the wellbore causes the turbulence, and it is two different kind of skin which is actually responsible for the distortion, right? So therefore, to estimate these two different skin components, we need to do multi-rate testing. We'll discuss this when we go to gas well testing, right? Next, multi-rate test with more than two rate provides data redundancy, which can be used for detecting insufficient cleanup and improve the data quality, right? So more the test we do, more the data redundancy can be eliminated, right? So it's also important for cleanup. So more the well multi-rate test will do, more the well will clean up, and also the data quality will improve, right? Now in this figure 3.6, what you can see, we have different multi-flow rates, right? Initially you have Q, and then the flow rate has increased, then decreased, then becomes zero. So there are a lot of variations, and there can be n number of variations, right? So this figure shows actually the n rate changes during production history. Now here the question arises is that what is the well bore pressure producing with this schedule, right? You want to estimate the well bore pressure. Now with such kind of schedule, it is very difficult to interpret that part actually. And to answer this, we have superposition principle, and it works in the same way as we have discussed in unit 1. Alright, so we will use superposition principle of logarithmic approximation to AI solution to answer such type of multi-rate analysis, right? So here what you can see, this is the equation which is for simple single flow rate, right? And if you try to modify this equation, what you can see here is that if you go on simplifying this equation, you have this simple function, right? So this Pi minus PWF is equal to m dash q log t plus s bar. Here the s bar is this quantity shown in the right hand side corner. Now here you can see the flow rate has been maintained constant. This is for single flow rate well, and this m dash is given by 162.6 mu b upon kh. So here m dash is not the same as m earlier. Here the m dash is not containing q anymore here. So you can see this pi minus pwf is a linear function of log t plus s bar. Okay, so this is the equation of a straight line if you plot pressure versus log t. Okay, so let's move on to principle of superposition, where you have seen that uh, there are different flow rates. Okay, and well is producing for different times. So this principle is very simple, and using this principle we can able to find out the pressure distribution, right? So equation number 10 that you can see here looks slightly complicated, but here I want to simplify this by uh, showing you some graphs. Okay, so here you can see, if we understand this in this way, that there are various production which is happening, as we have seen in our last slide. Multi-rate test, their flow changes every time, every durations. So initially there is a q1. Okay, so we consider that the flow is taking place at rate q1 for time t, right? So your first part of this equation will be m dash q1 log t plus s bar, which is same as for a well producing at a constant rate for time t, right? Now in the second case, what you'll see here is that in second case we'll consider that well is producing at different rate q2 minus q1, right? q2 minus q1. Now the elapsed time would be now t minus t1, right? Okay, so in this way we can go on and write for different conditions. So if we can write for this particular condition, what you will see here is that we have m bar q2 minus q1 into log of t minus t1 plus s bar. So here instead of t, now here the elapsed time is t minus t1, right? So we have put the value of t minus t1, and rest further we can make same assumptions, right? So in the third case, what we can do, we have q3 at time t2, right? So now t2 is from here to here, so the total time t minus t2, right? So this is the elapsed time for next production. So this is q3 minus q2, q3 minus q2. Okay, so in this way the series will go on, right? Now the same equation number 10 can be written in terms of slightly different, right? Although these two equations are same, however this is written in slightly different form, where qn is the total sum of all the rates, right? Qn. Now sorry, qn is the last rate, not sum of all rates. Qn is the last rate. Now this is the simple principle of superposition, and it is easily understood. Now if you apply this simple case for a condition where you can see that this qn is 0, right? Now when this qn is 0, let's think. This Qn is 0 in case of build-up test, right? So your last flow rate, whatever the past rate is, your last flow rate is 0. So you have to understand this, and if you put this particular thing in the equation, what you will do, what you will find is the simple equation of pressure buildup, right? So if this Qn is 0, there are different rates Q1, Q2 minus Q1, and at last what you'll see, Qn is absent, right? So in this particular part, you will see Qn is absent. As you can see, equation 10, there is Qn here. So you'll only have minus Qn minus 1, and there is no Qn now because the last rate is 0. Okay, so this equation takes this form. Okay. Now in this case, the n, if you take n equal to 1, right? Now n equal to 1 means, what is the meaning of n equal to 1? Single flow rate, right? So you are considering a single flow rate Q1 now. So you have, in terms of Horner approximation, if you say, whatever production history may be in the past, we are taking only Q last. And if we are taking Q last, right? So Q last will consider the cumulative productions in the past, and then we'll come up with a pseudo producing time. So here what you can see is this Q1 consider all the past flow rate, and this is the actual Q last, and T is the pseudo producing time, right? This T is the pseudo producing time. So we have arrived at this particular equation if we take n equal to 1. Okay. So similarly, you can understand this particular application and this particular application. I have written this for you. Okay, let's move on. Now sometimes we need this equation which is shown in this particular slide. What I have shown is pressure buildup preceded by 2 flow rates, right? So why do we need 2 flow rates? As we have said that in pressure buildup test, we are only concerned about last flow rate, right? So what is the duration of last flow rate? The last flow rate duration should be twice that of its preceding flow rate, right? And if it is not so, the pseudo producing time given by Horner's will not be applicable. So therefore, if the preceding or if the last flow rate, that is Q last, duration is lesser than its preceding rate, right? In that case, we should also take the preceding rate in our calculation. And once we do so, the equation is modified as equation 15, right? Equation 15. And if you put this equation 15 in terms of various properties, what you will see is this equation number 16, right? So when do we need this? This is needed when the Q last duration is not double that of its preceding flow rate. Therefore, we have to take or consider the preceding flow rate also, right? So this is the applicability of pressure buildup preceded by 2 flow rates, right? If you have any doubts, any question based on this particular slide, you can approach me anytime, right? Okay. Now this is a simple numerical which is considering the multi-flow test data for infinite acting reservoir, assuming minimal well bore storage, right? So in this particular question, the well bore storage part is eliminated and we are only left with the multi-flow rate test data which need to be evaluated, right? And what you can see here is that the time versus pressure, right? So this time and pressures are given. This pressure value is um, is your drawdown pressure, and this Qn, which is here, or you can also see here this Qn. So sorry for this. Okay, so here what you can see here, that you are given with the value of Q, right? So this is the average value of Q, that is average value of rate during first hour, right? So for first hour this rate has been averaged, for second hour the rate has been averaged, and for the third hour, for next 3 hours, the rate has been averaged 159, right? So what we have to do here, that you have to first point the plotting, first you have to generate this plotting function. Okay, so your plotting function is nothing but pi minus pwf, right, to this particular function. Now this particular function is nothing but this equation. Okay, so this is a multi-rate equation that need to be calculated here, and once you have this particular function, that is these two values, now these two values has to be plotted, right? And once we plot it here, what you can see is a straight line, this one. Now this straight line, the slope of this straight line is nothing but m dash. Now here m dash will give you the value of kh, right? Kh is the product of permeability and height of the reservoir, right? Perforation height, you can say. Next, the intercept on the y-axis will give you b dash, right? So if you take it from 0, whatever intercept you are getting on y-axis is nothing but b dash, right? Now this b dash is very useful in estimating the skin factor. Now you can see this equation for multi-rate flow. It is not similar to that of pressure buildup or pressure drawdown. Slight modifications are there. So this b dash is actually giving you the value of skin factor. So this b dash can be evaluated by the intercept on the y-axis, and this S can be estimated, right? So in this way, multi-rate flow test data for infinite acting reservoir can be estimated, right? Or we can estimate permeability and skin from multi-rate flow test data. If you have any question, any doubt regarding the calculation, you approach me, please. So next we'll discuss the analysis of type curve in the next particular online lecture. So I have to say bye here for now. Thank you.